Hello, welcome again. Today let us discuss about engine cooling. If you have understood the working of an heat engine, see here the heat engine always works in a thermodynamic cycle. For example, petrol engine works on Otto cycle, diesel engine works on diesel cycle. So that is what we call it as a thermodynamic cycle. There is always a high temperature source and there is a low temperature sink. By continuously burning the fuel, we can simulate high temperature source and we reject the heat to the atmosphere. That is what you can call it as a low temperature sink. The heat engine, whether it is CI engine or it is SI engine or petrol or diesel engine, takes the heat from the high temperature source, converts part of the heat into work and the remaining heat is rejected. So we say the first law of efficiency of the engine is work output of the engine, that is W, divided by heat supplied, that is Q1. W is nothing but Q1 minus Q2. So that way efficiency can be written as W by Q1 or Q1 minus Q2 divided by Q1. So that means it is impossible to construct an engine which converts all heat into work. So part of the heat has to be rejected. So where exactly this heat will go? In an engine, we circulate a coolant around this, around the engine cylinder. Part of the heat will go to the coolant. Part of the heat will be rejected through exhaust gases, correct? So some heat gets radiated, means out of the total heat Q1 entering into the engine, part of the heat is getting converted into work, some part of the heat is given to the coolant, some part of the heat is given through the exhaust gases, and some part of the heat is lost through various heat transfer processes like radiation. So in this chart I have shown, if there is 100% of heat is supplied to an engine, out of that around 33% will be lost through exhaust gases, another 30-31% to the cooling water, remaining will become indicated horsepower. Out of this indicated horsepower, some heat is lost to friction and other radiation losses, remaining gets converted into say brake power. Nowadays it is possible to achieve 30 to 32% brake thermal efficiency, means that is a useful efficiency. Now the question is, if we don't extract this heat carefully, the engine gets overheated and lead to lots of other problems. So how to cool this engine is what we will be discussing about. So this is what I call it as heat balance. You see, out of the 100% energy supplied, part of that energy, that is heat, will be converted into power. It will go to coolant, last through exhaust gas, last through radiation. Given it for 4-cycle SI engine, 2-stroke engine, again 4-stroke engine and gas turbines. You can observe here 4-stroke turbocharged engine, the efficiency is around 35%. 35% of the fuel energy supplied will be converted into useful work. If you look at SI engine, 4-stroke, 2-stroke, all these kind of these things are very efficiencies are low. That means heat losses. Now, why it should be cooled? If it is not cooled, first of all, between piston and cylinder we are using a lubricating oil. If the lubricating oil temperature start increasing, its viscosity will decrease. And first of all, between piston and cylinder, there is no oil film, then they start rubbing and erosion and damage of piston as well as the cylinder sleeves will happen. If the temperature is further high, even the lubricant oil gets burnt down. So a lot of carbon deposits will start happening. And another thing is, if the piston temperature rises very high and also the cylinder temperature, and if there is a differential expansion of the piston and cylinder material, so piston may over expand and seize completely. So what you can call it is the piston seizure may happen. Moreover, as the temperature increases, the strength of the various parts that we have used in making the engine, they lose their strength. So it is necessary that we maintain the right temperature by cooling the various parts of the engine. So already I mentioned, anyway, high engine temperature may result in very hot exhaust valve, which in turn may give rise to pre-ignition and detonation. If the cylinder head temperature is high, the volumetric efficiency and hence power output of the engine is reduced, because as the temperature increases, Once the gas enters, because of the temperature, the gas volume increases, and because of that, it will not be, the density decreases, volumetric efficiency is reduced. Another thing is, engine should not be overheated, engine should not be overcooled. If you overcool the engine performance will come down. If you cool too much, the lubricating oil viscosity will increase. Definitely energy is lost in overcoming, viscous forces. Thus, engine is not going to run very smooth. Second thing is, at low temperatures, because of the formation of various chemicals, because there will be sulfur in the gases, exhaust gases left previously, and these gases are cooled, then they become converted into acids. These acids attack the piston material, liner material, and they corrode. That's why the engine should not be overcooled at all. So, at least a minimum of 60-degree temperature has to be maintained, so that the wear can be minimized and also the corrosion can be reduced. So that is why as the engine heats up, its performance improves. So in this diagram, I have just shown graphically temperature distribution for operating in different cycles at different compression ratios at various points of the thermodynamic cycle. Also, what is the maximum pressure, what is the maximum temperature is shown over here. Now, if you look at these engine parts, if you take the piston side, see here the top, the temperature is around 230 degrees Celsius. As you come down near the piston rings and all, the temperature 180 degrees. As you go down, you see here, this is exposed to the flame. That's why the temperature is quite high in this region. As you go down, the temperature will decrease. If you look at the valve surfaces, you see here, this is the temperature distribution. You can see the temperature in excess of 500 degrees Celsius. Correct. If this becomes overheated and all those things, and when the air fuel mixture comes in contact with this will start acting as a spark plug. It has to be cooled efficiently. So this is like, these are for various types of size pistons, various types of engine. These are some of the data that are available showing the temperature distribution at various points. Okay, same thing, similar. So now the thing is, what are the parameters that affect the temperature distribution on these parts? One is heat transfer coefficient and combustion system. I'll explain what it is. The engine load, the type of cooling, whether it is air cooling or liquid cooling, low load or high load, what is the convective heat transfer coefficient present, what's the engine speed, what's the ignition timing, what kind of fuel air ratio, lean, rich, stoichiometric, high compression ratio or low compression ratio, inlet temperature, pressure, all these factors contribute for the temperature distribution on various parts, that is on the piston, then cylinder sleeve, valves, correct, all these places, right, temperature, right. Now let us talk about the heat transfer part. Now once the air fuel mixture is ignited, the combustion gets initiated, it starts burning. At the time of ignition, when the flame front is created, at the flame front the temperature is quite high. It is a adiabatic flame temperature. It's more than 2800 degrees Celsius. Anyway, as the flame front travels, the air fuel mixture gets burnt, hot gases are released, and as the piston starts moving towards the bottom dead center, expansion happens and the temperature will start decreasing. So now the thing is, whatever heat that is generated within this combustion chamber, part of it is responsible for converting into work. And these gases give heat to the various metallic surfaces through convection. And then the convected heat will pass through the solid surfaces by conduction. Again, this heat may be given to the coolant by convection. Again, coolant in turn may lose this heat to the atmosphere by convection, or again the heat might flow to the surface of the cylinder, and from there it comes in contact with the atmospheric air or give out the heat in the form of convection. So let us look at how exactly the heat transfer happens. Now this you consider the inside of the cylinder. So this part, let us call it as sleeve, this one, sleeve, okay. Here we have gases. This is the temperature of the gas. This is what you can call it as lubricating or stagnant layer of hot gases. Here the gases are moving. Here this is a stagnant layer of gases. This is the lubricating oil layer. This is sleeve, I said, metal valve, correct. Then you have the cooling water jacket. This is where the cooling water is flowing. And between this and this, there is a coolant water film, this one, coolant water film. So from the hot gases, heat is convected. Again, this is a convection heat transfer. This will offer resistance for the heat loss. Again, through the lubricating layer, again the heat is, passing through. It's a convection. Then it passes through this metallic wall. The heat is conducted. Again, heat is convected to the coolant. So now we can create a heat transfer circuit and we can find out what is the heat that is lost from inner layer to the coolant. Okay. So after making this heat transfer circuit, it is possible we can write the heat transfer equation as Q is equal to UA TA minus TC. This U is called overall heat transfer coefficient. U can be determined like this, 1 by H1 plus L by K, 1 by H2. This H1 you can say heat transfer coefficient, inside heat transfer coefficient, this outside heat transfer coefficient, thickness of the sleeve, cylinder sleeve, and K is the thermal conductivity of the metal. So if we have maintained very high heat transfer coefficients H1 and H2, and if you choose if the cylinder sleeve material thermal conductivity is very high and its thickness is low, then U can be very high. Overall heat transfer coefficient can be very high. This U and A is the surface area, TA inside temperature, TC is the coolant side temperature. So by manipulating, suppose if I can increase the U value, I can increase the Q value. If I increase the A value, then also I can increase the Q value. Assume that TA and TC temperatures are known, kind of a thing, known and fixed values. By manipulating this, it is possible to do it. For example, U can be increased by increasing H1 value or H2 value. These are heat transfer coefficient. Again, in the heat transfer you have studied that Nusselt number is a function of Reynolds number and Prandtl number for forced convection. So there again, looking at the various fluid parameters as well as parameters, it is possible to increase the H1, H2 value, and by choosing material of high thermal conductivity, it is also possible to increase the value of U. Okay. So by providing the fins on the surface, it is possible to increase A value. That way we can increase the Q value. That is the heat transfer model. Other heat transfer theory has been discussed over here, what material should be used and all that thing. So if you using these models, if you calculate something like that, if the gas temperature is around 850 degrees Celsius, it's a mean temperature, and the coolant temperature is something like 70 degrees Celsius. This is how the heat temperature profile will be. So this is, here I am using liquid coolant, that is water cooled kind of cooling system. Here air cooled, here we have provided a large number of fins to increase the area to enhance the heat transfer. And this is the temperature profile in an air cooled cylinder. So knowing the theory, engine cooling, now let us say the cooling systems. There are two types of cooling system, air cooling, other one is water cooling or indirect air cooling using water as a transfer medium. You call it as simply nowadays liquid cooling, and this is known as air cooling. So if you see, you must have seen in the motorbikes, scooters and all those kind of a thing, the outside surface of the engine cylinder will have fins and the heat is lost directly to the air, and the cooling system that we adopt is the air cooling type. In car, trucks, all those engines, we use coolant for cooling purpose. So it is a water cooled or liquid cooling. Nowadays we call it as a liquid cooling system. So this is what you can see, the air cooling system, where outside you can have number of fins. They can be of different shapes, size, made of different materials and kind of a thing like that to enhance the heat transfer. And you can also create paths so that the air circulation is maximum, so the heat transfer is maximum. So in liquid cooling system, right, so we circulate the liquid around the engine cylinder. So again you can call it as a thermosiphon cooling and forced circulation cooling. Suppose if you assume this is the cylinder block and is a heat exchanger, what you can call it as, if you want, radiator you call it. Okay, then there is a fan to force the air over this. Assume there is cooled liquid is available, and this is also filled with the coolant. Now once I start running the engine, the heat transfers from the combustion gases to this liquid. Now as this liquid gets heated up, its density decreases. So a natural convection current gets established. It will start circulating. Because its density decreases, it starts rising up. That will lead to a kind of circulation. Then this will draw high density water. Like this, continuously the high density water comes, takes it, its density decreases, rises up, comes here. As it passes through this radiator, air is blown over that, it loses heat, it cools down, again it comes here, takes the heat and so on. That's how you are creating. Here I am not using any pump for circulation purpose. The circulation happens only because of density gradient. That's why you can call it as thermosiphon cooling. Here we do not have much of control over the coolant, correct? Increasing the speed, decreasing the speed, all kinds of things like that. That kind of a control we do not have. In a modern engine, the thermosiphon cooling concept may not work. It is better we have a forced circulation system. Basically in a forced circulation system, what exactly that we have? Look, main thing is there is a pump here. There is a pump. Another thing is there is a thermostat here, correct? And also there is a coolant recovery tank. Okay. Now, let us discuss about these things. Whatever is indicated in the blue, it is a cooled liquid. This is a cooled liquid. It will be there. Gets into the pump. Next thing is what exactly that pump does is forces this liquid into the engine coolant jacket. Then as it passes through the coolant jacket, it gets heated up, then extracts the heat from the engine cylinder, correct, then rises up. Now there is a thermostat. If the engine temperature, suppose it is a cold season, engine temperature is, this coolant temperature is lower than the engine, the admissible temperature. So what I mean to say, it is something like that we are interested in minimum, like we do not want to overcool the engine. Say we want to maintain a minimum of something like 70 degrees Celsius. Then what happens, till this liquid temperature attains that value, the same liquid will be circulating like this. So it has come there, it will be circulating like this. Fine. Then what happens, what exactly happens, there is a thermostat valve here. It will be in the closed position, it does not allow that liquid to flow out like this. When we start continuously circulating, after some time, this liquid temperature increases. So now the engine temperature starts rising. So we have to circulate cool liquid here. Then once the temperature exceeds that value, actually the thermostat opens up. Then this liquid will flow like this, okay, gets into the radiator. So here you can call it as the top header of the radiator. This you can call it as the bottom header of the radiator. So it enters into the top header of the radiator, then it splits into a number of stream, and this hot water, as it starts, the air will be flowing over that, it gives out its heat to the air and it gets cooled, and again the liquid will start circulating like this. Okay, there is a radiator pressure cap. Boiling temperature of water is 100 degrees Celsius when the pressure is 1 atmosphere. So if we can maintain using a pressure cap little higher pressure, means if I can maintain a 2 bar pressure, then the boiling point will rise to 179 degrees Celsius. That means the coolant will be in the liquid state. If it is in the liquid state, heat abstracted is mCp delta T. Cp value of the liquid is always higher than the Cp value of the vapor. It will extract better heat. So using the radiator cap, we can maintain higher pressure so that it will remain liquid at high temperatures. So that the cooling process will be more efficient. Now the thing is, if something gets vaporized, this can flow into the coolant, correct? Right? By boiling, its volume increases, it can flow into this kind of a thing. When we cool the engine, again when the engine is switched off, when it is cooled, a vacuum gets created, again it will suck back into this and it will maintain its level. So this is what the thing is. Now the thermostat, when the engine is cool, so thermostat will be in the closed condition, it does not allow engine to overcool. Once engine gets overheated, it opens up and the cooling process, like coolant circulation happens through the radiator and efficient cooling of the engine happens. So the kind of coolant that we use nowadays, half and half propylene glycol or ethylene glycol and water. And there is a thermostat. You see here. Here the operation of the thermostat can be explained. This is like the liquid is not in the open position. You see here it is in the closed position. So from engine the liquid comes, engine bypass, correct, it like this. It is in the closed position, then it will go, circulate, again engine, it will come back like this. Here actually there is a spring loaded valve. This is held by wax, correct. So wax is now in the solid state. It will be holding this. Once this coolant temperature increases, this wax melts, then what happens is all of a sudden it opens up, right. It is in the compressed state, then it will expand. When it opens up, this will open up. So this valve will open up, then the coolant will start circulating through this one. Again when the engine is switched off, when it cools, again it will pull back. So that's how this thermostat works. Then a radiator, basically radiator is a heat exchanger. If you see the cut section of the radiator, you can see here, this is the top header, here the bottom header. You have a number of small tubes like this, small tubes, more than 100, 200 tubes will be there, arranged in a very zigzag fashion like this. So whatever liquid that comes is divided into smaller streams. Then each stream passes through this. As it passes through this, now we have a lot of fins to increase the area, heat transfer area. As the air flows over that, this heat will be lost by this hot coolant to the air and cools down. The coolant will come down here. From here again it is pumped to the engine. So you can say matrix you can have depending on the design, the heat transfer requirement and all those kind of the surface area requirement. You can have honeycomb type, ribbon type, tube and fin type, corrugated fin type and so on. These are the various types of radiator matrices. As I told you about radiator pressure cap and its importance. So now let us look at how exactly a thermostat works.
What we have sitting here is a thermostat. This is what regulates the water flow within the engine. As the cylinders are firing, it's creating heat and the heat is dissipated by water. This is going to stay closed until the water gets to a certain temperature, and then it's going to slowly start to pull open, and then once the cool water from the radiator comes into the motor, it's going to shut this back up and it's going to heat the water up again, and it's just going to be one continuous cycle. I can show you this with a simple torch. Now once it gets to a certain temperature, which I believe this one's 190 degrees, the air's starting to expand and it's starting to open the thermostat. Now what's going to happen is that cool water is going to come in and it's going to cool that thing off, and then it's slowly going to start to close again. And then the cycle just repeats itself by heating it back up and cooling it back off. That is all a thermostat does in your motor. It opens and closes to regulate the temperature of the motor.
So here the complete cooling system has been explained. Here the working of the radiator pressure cap has been explained.
If a coolant boils, it can be as serious for an engine as having it freeze. Boiling coolant in the water jacket becomes a vapor. No liquid is left in contact with the cylinder walls or head. Heat transfer by conduction stops. Heat builds up. And that can cause serious damage. One way to prevent this is with a radiator pressure cap that uses pressure to change the temperature at which water boils. As coolant temperature rises, the coolant expands, and pressure in the radiator rises up above atmospheric pressure, and that lifts the boiling point of the water. Engine temperature keeps rising, and the coolant expands further. Pressure builds against a spring-loaded valve in the radiator cap until, at a preset pressure, the valve opens. In a recovery system, the hot coolant flows out into an overflow container. As the engine cools, coolant contracts and pressure in the radiator drops. Atmospheric pressure in the overflow container then opens a second valve, a vacuum vent valve, and overflow coolant flows back into the radiator. And that stops atmospheric pressure collapsing the radiator hoses.
So far we have discussed about need for engine cooling, dangers of overcooling of the engine, the heat transfer process, air cooling system and the liquid cooling system. So we will stop at this point here. We will continue in the next video. Thank you.